Yes, hope you are able to see Word file, no? Yes, are you able to see this Word file?
Yes, sir.
Yeah. Okay. So today we will be discussing about this conversion of the continuous additive white Gaussian noise channel into a vector channel. Okay. Yeah. Before I take up this topic, hope everybody has solved the problem what I have given in the previous class. May I know what are the answers if you have done it? Yes, quickly, I want response from the people who have solved it. Yes, no answer means nobody has solved. Nobody has tried also. Hello. Yes, is it possible to respond whether you have tried or not tried?
Yes, sir, tried.
Tried. So may I know what are the answers?
Sir,
The value.
phi 1 of t, I've got it as 1 by root t from 0 to capital T.
Yeah, very good.
And phi 2 of t, I've got under root 2 by t from 0 to t by 2.
Very good. That's exactly correct. Fine. So hope when you are saying the value of pi 1 of t and pi 2 of t correctly, then other parameters, no doubt that you might have done right. What is the value of S11 you got?
Sir, S11 is a square t, sir. Sorry, meaning
Yeah.
a under root t.
Yeah, a into square root of t, right?
Yes, sir.
Yeah, a into square root of t over the interval 0 to t. Similarly, the value of S21?
It will be a under root t from 0 to t by 2.
Yeah, very good. So the value of S21 is a into square root of t over the interval 0 to t by 2. And then, okay, S21 you people have said. Then already pi 2 of t you have told means G2 of t you might have got properly, right? So the value of G2 of t will be equal to what?
A square t by 2 from 0 to t by 2, sir.
Yeah, the value of G2 of t.
Sorry, G2 of t is a from 0 to t by 2.
Yeah, correct. The value of G2 of t is a from 0 to t by 2 and its energy is a square by 2. A square into t by 2, right?
Yes, sir.
Yeah, a square into t by 2 over the interval 0 to t by 2. So with that, we can say pi 2 of t is square root of 2 by t over the interval 0 to t by 2. So if that is done, then so the problem is solved. Okay, at least one student is responding with right answers. I hope, I expect others also might have done in the same line. And even if you have not done, so today we have discussed the results, final results, right? So please do it, and I will put it in the GCR to upload. Okay, you all should upload that in the GCR. This problem, and as well as earlier to that, I think some 25% I have done, and remaining thing I have asked you people to do it now. So that problem also. So these two needs to be uploaded in the GCR today itself. Okay, fine. So and another thing is, you all know the internal, first internal is going to be conducted from what date? Yes, why nobody is talking? Yeah, from 28th. Yeah, from 28th, your first internal will be there. So first subject will be this, right? So digital communication. So tomorrow I will be discussing about this case study and innovative questions. Okay, what to study for case study and what to study for innovative. So whatever I discuss till I think Wednesday, so that will be there for your test, for the first test. Okay, fine. So with this understanding, let me continue the next topic. So, which is what I said, conversion of the continuous additive white Gaussian noise channel into a vector channel. So, with this, maybe okay, it may be new to you all, but most of the things are known. Okay, most of the things are known. So I expect you people to answer here and there when I am writing the equations. Okay, it is not completely unknown. So here what I am saying is conversion of the continuous additive white Gaussian noise channel into a vector channel. So we have discussed how we can represent a signal or M of finite energy signal into a signal vector, right? In the similar way, here we are going to do the conversion of this AWGN channel into a vector channel. So vector channel means similar to the vector signal vector. What I wrote SI is equal to what? SI1, SI2 and so on up to SIN. No? Yes or no? In the same way, we expect you here to derive an expression for that, for the channel. Okay, so let me begin with this. Okay, so to start with, so how do we just write the uh, channel, model of a channel? Anybody, any idea is we have? How do we write the additive white Gaussian model of a channel? Yes, no idea? Okay, so let me begin with this. Okay, so what I said, yeah, I used to say SI of t is my transmitted signal, right? SI of t is the transmitted signal. So let me write SI of t is what I said, it is the transmitted signal. Okay, so SI of t is the transmitted signal. Or let me run this. Okay, I wanted to say SI of t is the transmitted signal. Then this transmitted signal will be passing it through the channel, right? So I can write this channel by, usually we denote, okay, and we indicate the noise, okay, will be at the channel. Okay, it will be adding the noise at the channel. So this we call as a white Gaussian noise. White Gaussian noise, so which will be denoted by a letter W of t, or variable I can say as W of t. Okay, so this is the white Gaussian noise. So this is the transmitted signal, and this is the white Gaussian noise will be added in the channel. So output will be what? This will be the received signal, what I can say. Hope we are able to visualize this. So this I denote as x of t. So this x of t is my received signal. Okay. X of t is the received signal. Sorry. Okay, let me write with a different color. Yeah. So this is my received signal. Okay, so this is the additive white Gaussian model of a channel, what I can say. Okay, additive yeah, hope you people have written. So this figure I say is what I said, additive white Gaussian noise, AWGN model of a channel. Okay, AWGN model of a channel means I say what is the transmitted signal. I said the transmitted signal will be represented by SI of t, right? I do this. I use this summation symbol to indicate that the transmitted signal and the noise. That noise I am considering it as white Gaussian noise, which I denoted by W of t, will be added in the channel. So output of that channel will be the what received signal, which I denoted by a letter X of t. Okay. Hope I am clear. How do I write the model of a channel? That to additive white Gaussian noise model. Yes, I am asking, is it clear?
Yes, sir.
Yeah, please, if people should note down this. I think now I am writing in a Word file. I can share the PDF file of this. Not an issue. Fine. So having this knowledge, right? How do we write the additive white Gaussian noise model of a channel? Then I think we have discussed about the analyzer. Anybody is remembered analyzer? What is analyzer? Is it possible to say? Synthesizer and analyzer, two things I discussed, right? Maybe even in the first module also, and even in the second module also, I represented SI of t. How do I represent that? It is a summation of what? J is 1p and Sij pi j of t, right? How do I get those coefficients? Sij, that is Si1, Si2, and so on up to Sin. Similarly, that is from Sij to Si of t is the input signal. How do I get the coefficients? I said, right, by passing it through a correlator, right? Then from coefficients, how do I get the Si of t also? So both the things I have discussed, right? Hope you people have remembered that diagram, synthesizer and analyzer.
Yes, sir.
Yeah. So with that understanding, here what I wanted to say is the input. Okay. There, what I said in case of analyzer. Okay, Si of t is the transmitted signal, right? That from that I was able to obtain the coefficients, that is Si1, Si2, and so on up to Sin by passing it through the correlators, I said, right? Bank of correlators. So here I am giving the received signal. Okay, so here what is the received signal? X of t, right? So which is equal to, from this above block diagram, what I can write, X of t is equal to Si of t plus W of t. Can I write like that?
Yes, sir.
Yeah. So this is what I wanted to convey. So X of t is the input to the bank of n correlators. Okay, I have n correlators. For that, input is what? X of t. So from that, I am going to obtain the coefficients. Let me see that. So let me say this in a proper way. That is, the input to the bank of n product integrators, or what we call it as a correlators, is the received signal x of t. Okay, so how do I define that received signal x of t? In accordance with the above diagram, that is based on additive weight Gaussian noise model, I can write x of t. Can write x of t is equal to. Yes, anyone of you can say what can I write? X of t is equal to.
Si of t plus W of t.
Yeah, Si of t, which is the transmitted signal, plus W of t, right? Plus W of t. So let me call this as equation 1. Okay? And this exists over the interval what? 0 to t, right? So let me write that interval also. Means that x of t exists over the interval 0 to t. And I can say the value of I can vary from 1 to m. Okay, so let me call this as equation 1. So this is my equation 1. Okay. So okay, in this, what I can say, what is Si of t, and what is W of t, right? So W of t, I think here two things I need to clarify. One is with respect to I represent small w of t, right? I think you should be able to understand if I write capital W of t is what and small w of t is what with respect to this random process. Are you aware of that? We use capital letter for what and the small letter for what? Yes? Hello? Hello? I'm not getting any response.
Capital letter is usually for mean, sir.
Capital letter is usually for mean. Okay. Then? And then what else? Yeah, here two things are there. Okay. Okay, what you said is fine. So, are you, I think, able to visualize there is a process, there is a random process, right? In that the sample values will be written by small letters, right? Sample function, what I wanted to say. Okay. So let me here write capital W of t. Okay, here capital W of t is the what? This one is the white Gaussian noise process. Okay, white Gaussian, white Gaussian noise process. This is a random process. Okay, noise process. And if I write small w of t is what is the sample function. Is the sample function of the random process capital W of t. Okay, sample function of the white Gaussian process W of t. Is that fine? Yes, able to understand what I am saying? Hello?
Yes, sir.
Okay. Fine. I said what is capital W of T? It is the white Gaussian noise process with zero mean. Okay, with the zero mean and having an power spectral density of how much? N naught by 2. Okay, so let me write W of T. So W of T is the what I said, white Gaussian noise process. Yes, hope you are able to see my rating now. Hello.
Yes, sir. Visible.
Yeah.
Yes, sir.
Yeah. Visible. Okay, so I said the capital W of T is the white Gaussian noise process with zero mean. Okay, with zero mean and power spectral density of N naught by 2. Okay, power spectral density of N naught by 2. Okay, so now let us try to find the output of the correlator, right? So output of the correlator. So I think before I write this, let me draw the diagram so that you will be able to get that visualization, right? So let me say, yeah. So let me write. So I said the x of t is my received signal, right? X of t is my received signal. From this, I need to get the coefficients, right? I said. So I am going to apply this to the n number of correlators. Okay, n number of correlators. So I need to draw that n correlators. So first, let me draw the first one. So what is correlator? Any one of you can say correlator?
So
Yes,
can you
quickly.
scroll on top, sir?
Pardon?
Can you scroll on top, sir? Little bit?
Yeah, okay. So I wrote that about W of T. So
Sir, but you had written another thing, sir. So sample
yeah,
function. What about that?
yeah, yeah. That is what. See, small W of T is the sample function of this Gaussian process, white Gaussian process. Okay, with what?
Okay.
Zero mean and power spectral density of N naught by 2. Two things are there. So this is basically a random process. In that, the sample function is small W of T.
Okay, sir. Sir, you have written small w or the capital, sir?
Here it is small W of T. Okay, so let me write it properly. Yeah, let me write. This is the small W of T. Okay, is the what? White Gaussian noise process. Here I can write capital W of T. Is that fine? Capital W of T. Let me write it clearly. Yeah. So this was small W of T is the what? Sample function. Okay, it is the sample function. It is the sample function of white Gaussian noise process, which we denote it as capital W of T. Okay, capital W of T. Of what? Of zero mean. Usually we consider it is having zero mean and the power spectral density of N naught by 2. So this is by definition of the white noise. Okay, it is having a zero mean and a power spectral density of N naught by 2. I hope are you remembering the power spectral density of white noise? Just we write the frequency as x-axis and we write one line, right? It's almost the Fourier transform of a delta function. Hope you are aware of that. Power spectral density of white noise. Yes. Yes, is this clear? I said small w of t is what? Sample function of the weight Gaussian process, which I denoted by capital W of t of 0 mean and possible density of n naught by 2. Okay, so now I was asking about the correlator, right? So x of t is my received signal. See, from this I need to derive what I said, the coefficients, right? So x of t is my what? Transmitted signal plus noise. Both the things are there. Okay, not only the transmitted signal. X of t is having two things. One is transmitted signal, which is Si of t. Another one is the noise. Okay, so I was talking about correlator, right? So any one of you can say what is correlator?
Product modulator followed by an integrator.
Yeah, product modulator followed by an integrator. So I can say here there will be a multiplier, right? So for this, the basis function is pi 1 of t, I can say. So I can have n number of basis functions, means n correlators will be there. So output of this modulator is given to the integrator. Okay, it will be integrated over the interval 0 to t into dt. So together we call this as what? Correlator, right? Multiplier followed by an integrator is known as what I said is the correlator. Is that fine? If I write here, this one we call it as a correlator. Okay, so what will be the output of this correlator? See, input is x of t, right? Another input to this multiplier is pi 1 of t. Then that will be integrated over the interval 0 to t. So here I can write output of this as small xj. This small xj is a what? Sample value of the random variable capital Xj. So I write the random variable just with a small letter, that is RV, means random variable. Okay, this is my Xj, capital letter I am using. Is this fine? Capital Xj is the random variable, and small xj is the what? Sample value of this random variable. Hope I am clear. Small xj is the what? Sample value. Sample value. Sample value of the random variable capital Xj. Okay, small xj is this. So what is this small xj? I can write this one, no? This is a random variable xj. I will come to that. So I think I will use a different color and let me write. So if I substitute j is 1 here, right? So I can write the random variable x1. The random variable x1 will be equal to what I can write is si1 plus w1. si1 plus w1. I will tell how I got this one, si1 plus w1. So that is our goal to derive. Okay. So like this, I can have n number of correlators. So similarly, you can write the second correlator also. Okay. By saying it is pi 2 of t, then modulator pi 2 of t integral 0 to t into dt. So here you can write what? This will be your x2. So first one I said it is, since j is 1, I can say it is a small x1. Okay. Then this one is what? x2. So I wrote here general xj, and capital Xj is random variable, right? And what is when j is 1, x1 is equal to si1 plus w1 I said this small xj is the sample value of the random variable xj. Okay. In the same way, you can write what is x2. It is si2 plus w2. Okay. So like that, you can write up to for n number of correlators. Okay, so I think I can put a dotted line. I can say you can have n number of correlators. So let me write this is my pi n of t, where the value of j can vary from 1 to n, right? Then you write integrator, so 0 to t into dt. Then this will be what? Yes, what is the variable I can write here? Small xn, right? So which is equal to, in terms of random variable, I can write capital Xn. Okay. So with respect to this, I can write here that is xn, that is capital Xn. Okay, capital Xn will be equal to sin plus small w n. Yes, is this fine? I have understood this diagram. Just it is an analyzer. So x of t is my received signal. Okay, this is my received signal. So I already wrote what is x of t. X of t is equal to si of t plus the additive white Gaussian noise. That is w of t I wrote, right? So this is a received signal. From this I am going to get back the random variables, right? How do I get that one? By passing it through the correlators. So basically it is a demodulator circuit. What I wanted to say here is, okay, x of t is multiplied by this carrier, then pass it through an integrator, then you will be getting these sample functions. Okay, so I think this is what I said in this. This one is only we are calling it as an analyzer. Hope you understood this point. This figure is the analyzer diagram, what I can say. There, I wrote with respect to si of t. Okay. Here I am writing with respect to x of t. Yes, I think you need to spend some amount of time for. I will take you to understand these things. Why I am writing what is random variable. I am writing a capital Xj. I said the value of j can vary from 1 to n. Then I am saying its sample value, which I denoted by small x, right? So that is small xj. Again, the value of j can vary from 1 to n, right? And I said what is this capital? There is a random variable xj, which I can find out it as xi1 plus w1. Means this has the transmitted signal and as well as the noise. Okay. Yes, hope you are understanding what I am saying. Hello. Yes, are you able to understand what I am saying? Hope you written this diagram, analyzer diagram. Yes, my dear students, please respond. No, are you
Yes,
there
sir.
Yes,
with me?
sir.
Yeah, I will. Miss, as we go further, you will be able to understand. Okay, at least you are aware what is analyzer. I am telling here with respect to the received signal. Okay, fine. So once we are aware of this thing, then let me say next is I told what is x of t, right? X of t is si of t plus w of t, I said. So output of every correlator, right? I denoted as xj, right? Output of the correlator. Let me write here the output of correlator, which I denoted as xj. That is small xj. Okay, output of the correlator xj. As I said, this is the what? Xj is the sample value of the random variable, sample value of the random variable random variable. How do I denote that random variable? I denote that by capital Xj. Okay. Then how do I define this small xj? It's a sample function, no? How do I define the sample function xj? Yes, is it possible to say? I said small xj.
Scroll up.
You want me to scroll up? Okay. Yeah, is it fine? I said the out. Huh?
Yeah.
Yeah, I said output of the correlator. I denote it by small xj. Small xj. Okay. What is the small xj? Is the sample value of the random variable capital Xj. So capital Xj is the random variable. Its sample value I denoted by small xj. So how do I define the sample value? Maybe from the diagram, I think you will be able to tell what is small xj. There is a sample function. Is that fine if I move up?
Yes, sir.
Yeah. Just let me write. Yeah. Any one of you, is it possible to say how can I write the sample value equation? Yes, looking at the diagram, you can't say. Whose sample value?
Integral 0 to t x of t into phi 1 of t dt or phi 2 in general phi j of t dt.
Yeah, very good. So that is what, right? So I can define xj, small xj. Okay, small xj. That is what is the sample value or sample value of the random variable capital Xj, which is equal to what I can write, integral 0 to t, right? Integral 0 to t. What is in one input? It is x of t. I'm writing it general. If it is x1, then would have written x of t into pi 1 of t, right? So to make it general, I'm writing it is pi j of t into dt. Is this fine? Yes, you all agree with me? The sample value, which is denoted by small xj of the random variable capital Xj, is defined like this. Xj is equal to integral 0 to t x of t pi j of t into dt. Just if you see the diagram, you will be able to write this expression. Yes, any doubt in this? Because one input is x of t, another input is pi j of t. Just I'm integrating that over the interval 0 to t. That is the, what I can say, the sample value of the correlator. Okay. Yes, is this clear? Yes, I'm asking, is this clear or do you have any doubts?
Yes, sir.
Yeah, very simple to understand if you have that diagram in your mind. Hope you are noting, na? Everybody is noting? Yeah. So now let me substitute x of t here, the value of x of t. What I said, what is the value of x of t? Integral 0 to t. Yes, any one of you can say what is the value of x of t? Value of x of t.
Si of t plus
I of
w.
t plus w of t.
Yeah, I am repeating so many times. Si of t, right, plus w of t, right? So entire thing is multiplied by pi j of t. Okay. Pi j of t into dt I can write. Is it fine?
Yes, sir.
Yeah. So now what you can do is you can split the integration and you can simplify further, and let me say what is, means I wrote now what is xj is, right? So let me write that. So what can I do now? Next step. So if I split it, yes, any one of you can say what we can write. The integral 0 to t Can I write first term as Si of t, pi j of t into dt? Is this fine?
Yes, sir.
Yeah. Similarly, then second term, what I can write is is what I can write 0 to t, right? W of t then pi j of t into dt. Is this fine? Yes, I'm asking, is this fine? Just I wrote Si of t pi j of t into dt plus integral 0 to t W of t pi j of t into dt. So what is this one? Integral 0 to t Si of t pi j of t into dt?
Yes, Ij.
Yeah, very good. So the first term, integral 0 to t Si of t pi j of t into dt can be written as what? Sij. So that is what is your coefficient, Sij. Fine. Plus, in the same way, I can write this as what? Integral 0 to t W of t pi j of t into dt as Wj. Another coefficient for noise it is, right? Is this fine? So I'm denoting what is Sij and what is Wj. So where the value of j can vary from 1 to n, right? Where the value of j can vary from 1 to n, 1, 2, and so on up to n, I can say. So let me call this as equation 2. Yes, hope you have understood why I wrote at the beginning, means while writing the diagram, I said no, xj is equal to Sij plus Wj, right? When j is 1, I wrote Si1 plus W1, right? Similarly, for x2 is Si2 plus W2 and so on up to xn can be written as Xin plus Wn. Is that clear? Yes, is that clear? I'm asking. I think the diagram is there in the previous page. Hello? Here is the diagram, right? Yeah. Yes, is this clear? I'm asking. X1. See, capital X1 is nothing is equal to small x1 I can write, right? Which is equal to Si1 plus W1. Yes, hope this point is clear.
Yes, sir.
Yeah, then already okay. So what do you understand from this? Out of these two signals, which one is deterministic and which one is non-deterministic? Is it possible to say which signal we can call it as a deterministic signal? Looking at these two terms, hope you understand what is deterministic and what is non-deterministic. Yes, are you aware what is deterministic? Yes, I want response. See, these are all the basic things which you have studied, no? Signals, different types of signals you have studied, right? In that way, I'm asking. See, I wrote xj is equal to two terms, right? One is Sij plus Wj. Out of these two, which one I can call it as a deterministic signal or component, and which one I can call it as non-deterministic signal? So not possible to say. Deterministic means what? I know what is I have transmitted, right? I can call this one is the deterministic signal. Okay, Sij is the what? Deterministic component of Xj, I can say. This is the deterministic component. Deterministic component of Xj. Why I call that as a deterministic component? Because that is this Sij is due to what? Yes, Sij is due to what I get? Due to what term I get? I get this one Sij due to the transmitted signal. Due to the transmitted signal Si of t. Can I say that? From Si of t, I get Sij as a coefficient, right? But this one is what? This is a noise. Wj is a noise. So which is added in the channel. That I don't know what it is. Means how it looks like and all, right? So that is why I say this Sij is the deterministic component of Xj. Okay. That is due to the transmitted signal Si of t, I said. So then we know how to find Sij. Yeah, quickly, any one of you can say what is the expression I can write for Sij? Sij. Yes, already we know how to find Sij, the coefficient.
Integral 0 to t is I
Yeah.
of t phi j of t dt.
Yeah, integral 0 to t Si of t phi j of t into dt. Is this fine? Yes, I'm asking, is this fine? Hello, can I write Sij is equal to integral 0 to t Si of t phi j of t into dt?
Yes, sir.
What is this, man? See, only few people are responding. What others are doing? See, this is the known fact or not? Do you think that it is coming from anywhere? So this I discussed in last 4 or 5 classes, right? While doing this Gram-Smith orthogonalization procedure, how do I write the expression for Sij? So you should be able to respond for the known things. Okay, I will call this as equation 3. Okay, so this is equation 3, I can say. Fine. In the same way, this is what I said, Sij is the deterministic component of Xj due to the transmitted signal Xj, due to the transmitted signal Si of t, right? So similarly, Wj, okay, so Wj is what? Wj is the what? Is the sample value of Wj is the sample value of the random variable. Just I will like RB random variable the capital Wj. Okay, this is a small Wj. What I wrote it there is the what? Sample value of the random variable capital. So this is due to what? Due to channel noise. Due to channel noise W of t. Due to channel noise W of t. Okay, fine. So how do I define that? Yes, similar to that, people can say, how do I write that Wj expression?
Integral 0 to t W of t into phi j of t.
Yeah, whatever I wrote there, I am again rewriting that, right? So integral, I can say 0 to t W of t, right, phi j of t into dt is my Wj. Okay, so let me call this as equation 4. Call this as equation 4. Okay. Fine. I think hope a few things are fine as of whatever I have discussed so far. Is it possible to sum up what I have discussed quickly? Yes. I will stop presenting. Sorry. Yeah, quickly, I want any one of you to sum up what I have discussed so far. Yes, some people can unmute, no? So, Anand, Namita, Chandana, and all. They are unmuted. Please mute it, otherwise, I think it may be disturbance for others. Yes, already Diksha is writing a reverse sign in the chat box. Yes, hope are you able to hear Anand? Anand, Namita, Chandana. Please mute your microphone. Yes, still Chandana also not here. I think Namita also not here. Yes, who can sum up? Yes, Chandana, can you do the summary? What I have discussed? Chandana.
Yes, sir.
Yeah. Yes, quickly you should summarize because time is up. Let me find up. Yeah, be fast. What I have discussed, is it possible to say
Sir,
quickly?
we discussed about the conversion of the continuous wave.
Yeah. Yeah, just tell me in brief what it is. How do I write the additive weight Gaussian noise channel model?
Where
AW.
transmitted signal and white Gaussian noise are both added together to get the received signal. X of
Okay.
t is xi of t plus w of t.
Very good, very good. So that received signal, which we denoted by x of t, which is equal to the transmitted signal Si of t plus the white Gaussian noise, which we denoted by W of t. Fine. Then I said, how do I find the sample value, right, of the random variable xj? So small xj is a what sample value of the random variable capital Xj. So which is equal to what I can say. Others should respond. Namita. Yes, what about Rohit Joshi? Can you tell me how do I define the sample function xj? Rohit Joshi.
Yes, sir.
Yeah, can you just tell me the expression for the sample function or sample value of the random variable xj?
So not able to recalling now, sir.
Not able to recalling now. Yes, anybody else? Anybody else I'm asking? Other than the people who are interacting regularly. Yes, quickly, time is up.
Sir, xj is
Ah.
equal to Sij plus Wj.
Okay, you told final answer, but as an integral part,
So integral 0 to t x of t into phi j of t into dt.
very good. So we begin with that, then we substitute the value of x of t as Si of t plus W of t, then we come to that value, right? Xi is Sij plus Wj. Then what I said, Sij is the deterministic component of xj due to the transmitted signal Si of t, and Wj is the what I said is the sample value of the random variable Wj, capital Wj, that is due to channel noise W of t. Okay, so let me stop with this. Continue in the next class. Okay, I will take the attendance.